Okay, so I think we can start our afternoon session. Somewhere it is afternoon, somewhere it is morning. So and I'd like to present Carlo Iazeolla, who will talk about boundary conditions, ordering, and Fronsdal fields in Vasiliev's higher spin gravity. Please.
Okay, so thank you so much. And let me start by actually thanking the organizers for, first of all, making the effort of putting together this workshop and giving me a chance to give a talk. So in this talk, what I would like to do is to briefly take you through some of the recent progresses in high spin gravity coming from the analysis of the nonlinear equations that have been written down by Misha Vasiliev. And in particular, focusing on some ideas that concern different perturbative schemes and how to impose boundary conditions in different perturbative schemes. This is actually related, I hope I will be able to say something about that, to various hot topics in the field at the moment, such as analysis of vertices and of high spin fields and the computation of boundary correlation functions from the observables of the Vasiliev theory. So, first of all, high spin gravity is essentially the dynamics of an infinite multiplet of gauge fields of all spins. It's been conjectured to be dual to some of the simplest system one can think of, essentially free CFT. And it is interesting because it is a system of intermediate complexity between that of the full string theory and supergravity plus higher derivative corrections. Essentially, it is a system which is very constrained because it has infinite dimensional local symmetries, but at the same time is quite far from ordinary field theories. Number one, because the order of derivatives in a vertex grows linearly with spin, and it is therefore expected the theory to contain non-local interactions. And also all the fields are actually on equal footing, and that means that concepts pertaining to the standard Riemannian geometry lose meaning in the high spin covariant theory because they are not higher spin invariant. So a proper understanding of higher spins should provide us also with an understanding of what would be a proper stringy generalization of geometry. So, sorry. Yes, so given the state of affairs, it is actually remarkable that one can still control many features of the nonlinear theory, essentially due to the infinite dimensional symmetry that govern the theory, and due to the compact form of the nonlinear equations. And in this sense, this suggests, actually many authors have suggested in this perspective, that much insight can be gained on the most pressing open issues of the theory by addressing them within the natural framework of the equations in terms of the high spin covariant variables that the equations are that feature in the equations, and corresponding high spin invariant observables, rather than in a more familiar setup of the language of spin S component fields somehow. And this is actually the spirit in which I'm going to exploit in this talk for a proposal for a perturbative scheme and how to impose boundary conditions on the field, asymptotic AADS boundary conditions on the master fields of the equations. So let me then briefly recall what is the formulation of four-dimensional bosonic Vasiliev's equation. So one can think of Vasiliev's equation as a generating system for fluctuations, for space-time nonlinear equations that involve gauge fields of all spins. And they are formulated in terms of so-called master fields that not only depend on space-time, which would be little x there, coordinate, space-time coordinate, but also on a pair of oscillators, y and z, that are non-commutative. They actually satisfy a Heisenberg algebra. Hope you can see my cursor here. Heisenberg algebra among themselves, y among themselves, z among themselves, and y and z are mutually commuting. And they are essentially, as before, are quartets. Sometimes I will use the capital Y, a capital Z, sometimes the little y and little z, which in this case denote their SL2C components. But anyway, it's just a notation. Now, the Y variables essentially will turn out to be fiber coordinates, in the sense that the spin S generator can be realized as a degree 2s-1 totally symmetric monomial in Y. Whereas the Z variables, we will see what their role is, essentially can be thought of more as a non-commutative extension of the space-time manifold. So the three variables that enter the Vasiliev equation are these three. U is actually a one-form connection, which contains gauge fields of all spins plus auxiliary fields. Phi is a zero form, and that contains, we will see, the Weil tensors and their derivatives. So essentially, phi contains the local degrees of freedom, propagating degrees of freedom. And then there's another connection, which is a one-form connection in Z space, which is auxiliary as far as local degrees of freedom are concerned. It doesn't contain any extra local degrees of freedom. Okay, so in terms of these variables and of the Z differential, which I denote with this Q hat, which is essentially just a commutator with Z, the equation takes on a remarkably compact form. Essentially, you see that all fields are subject to zero curvature or covariant constancy condition, but for the pure Z space direction. So U is actually a flat connection. Phi is covariantly constant with respect to both the U spacetime connection and the V Z space connection. The combination Z plus V is covariantly constant with respect to U spacetime connection. And the only non-trivial source of curvature actually is in the pure Z space curvature, QV plus V squared. And it is, the source term is in fact phi itself times spacetime constant 2 form in Z space source, which is this J, that contains this operator kappa, which turns out to be a sort of intertwiner between the representation that phi belongs to and the representation that V belongs to. But this kappa will be of interest later on, because you see that it's essentially the essential part of the source term, but for phi. And interestingly, it is an operator that is factorized into a similar operator that only operates on Y, and another that only operates on Z space. And all these operators do is anti-commute with Y's, respectively, for kappa Y and Z for kappa Z, and be involutive. So they are essentially, they can be represented as -1 to the number operator in Y or Z space that counts the number of Y's and Z. Okay, so the spirit of this equation is that Z oscillators are actually non-commutative coordinates, and the equations, in particular this equation, the most juicy one here, solves Z contractions of the fields in terms of curvature of the physical fields contained in phi. And this triggers a whole infinite tail of gauge invariant and linear interactions in terms of the physical fluctuation fields that are contained in the integration constant for the Z equations for U and for phi. And these integration constants we're going to refer to as W and C. P I simply denote by P a projector on the Z cohomology here, but more details on this will come in due time. What we want to do now is to set up a perturbative expansion on anti-de Sitter. I mentioned anti-de Sitter because that's the simplest actual solutions, vacuum solution of the equations. And in fact, it's singled out by setting phi to 0. Phi contains the Weil tensor, so this essentially means Weil flat. This Z-space connection V also 0, and U which is a flat connection always, can be represented in this case via a gauge function that is essentially an ADS4 coset element as L-1 dl. So this is pretty standard. And starting from this vacuum solution, one can set up a perturbative expansion around it. The idea is that because this vacuum solution is singled out by phi being 0, now this perturbative expansion can be actually organized in a perturbative expansion in expansion in the curvatures that are contained in phi at first order. So let's call this this C, integration constant. We will see that this is actually the case for the Z evolution, will be only dependent on X and Y. And the orders of every field here, U, V, and phi in this order N is actually, will turn out to be order N in these curvatures contained in C. So the equations essentially lend themselves to be integrated iteratively in this expansion in curvatures. And if you take a look at the form, look at all the equations that contain a Q, so a Z space differential here. All these equations that control the dependence on Z are of the form Q on something equals something else, obviously. And the idea is to solve equations of this form via some proper inverse of this Q, a resolution operator Q star, which will give F in terms of Q star G, and that is essentially a particular solution, plus a solution of the homogeneous equation, which will contain a pure gradient gauge that controls the gauge symmetries, and a representative of the Q cohomology, so an integration constant for the Q differential here. Okay, so we want to do now this analysis. However, this is facilitated, obviously. First of all, it is important to go to an ordering prescription in order to have a non-trivial a fixed basis in our operator algebra here of Y and Z. Second, the analysis is facilitated by mapping every basis element of this ordered basis to a symbol, so to a function of commuting variables that essentially represent this operator in terms of ordinary functions. One can consider, in fact, linear invertible maps between spaces of function of commuting variables, which we refer to as symbols, and operators in a given ordering. These are actually invertible, so to every f hat, let's say, that will correspond in a given ordering, will correspond an f, 1-to-1. And this correspondence actually induces an algebra isomorphism, where the operator product will be represented on these spaces of commuting function via a star product, non-commutative, which is concretely realized on symbols via convolution. The particular form of the convolution, of course, depends on the chosen ordering, but now the details of it won't be important. Let me just mention two orderings which will be useful for this perturbative scheme. The ordinary perturbative scheme actually makes use of normal ordering. It's not important exactly the form of the convolution, just there is a well-defined convolution in this case. Normal ordering between the combinations y minus z and y plus z. And in this particular ordering, y and z are sort of maximally entangled. There are non-trivial contractions from y star z. And what's important is that in this ordering, this total Klein operator that you see as the on the right-hand side, the only non-trivial source of the equation, is actually a regular operator. It's just an exponential of y and z. On the opposite end of the spectrum, somehow, there is Weil ordering on the total yz space. Opposite end because in this ordering, there are no contractions between y and z. So the star product of such functions is represented as, of a function y, star a function with z, is just the ordinary classical product. And as a consequence, it turns out that the Klein operator in this ordering becomes a delta function. So it's going to be a singular operator. And in fact, let me mention that for various reasons, a couple of which I'm going to mention, extension of this perturbative analysis to a whole family of orderings and interpolates between these two orderings have been considered recently. Now, once we have chosen an ordering and corresponding symbols, then the analysis gets easier, because in terms of symbols now, Q is just the RAM differential on Z space, and therefore one can actually write down concretely a form for this resolution operator Q star. So a particular solution to an equation that looks like QF equals G can be given by homotopy contracting actually along Z, and this Z can be shifted by any Z-independent vector, it turns out. So the actual form is not important, but what one should keep in mind is that there is an intrinsic ambiguity in choosing this resolvent operator, this Q star. And this ambiguity in choosing the contracting direction along Z shifted by any vector psi amounts to actually, it's what controls different gauge choices and at the same time field redefinitions. The simplest choice, of course, in this operator is choosing this psi to be just 0. So in this case, I homotopy construct only along Z. And this corresponds to the standard choice made in perturbative scheme. It has the advantage of simplicity, but it has some disadvantage that I will comment on very quickly right now. So let's look at this expansion in first order, actually. So the standard perturbative expansion of the equation in normal ordering and this easy form for Q star, which I will refer to this label E, looks as follows. So at the first order, you see that first of all, Q of phi 1 is 0. That means that phi 1 is purely X and Y dependent. And this is a universal feature of the expansion around anti-de Sitter. And it is covariantly constant. Okay. On the other hand, once one uses this solution, one can put it inside this other equation that determines V1 in terms of phi and its source J and the source J, and can resolve by this choice of Q star. And V1, therefore, becomes a particular solution for V1 is given in terms of phi plus a pure gradient, of course. Sticking this solution inside the equation that determines the Z behavior of U1, of the space-time connection, one finds that this is solved in terms of the original degrees of freedom in phi, plus a Z constant, plus some, of course, gauge freedom here. Now, the simplest gauge choice one makes is the so-called Vasiliev gauge, that is to say, setting Q epsilon here to 0. And if one does that, takes these two solutions, V and U, sticks them into the remaining equations, which is this equation D0 of U equals to 0, obtains actually, you see that D0 now hits on this term and on this term, giving 0 on this term because D0 squares to 0. And obtains the following free field equations on X times Y, so space-time with the fiber Y. Just the first equation here on C is very simple. It's covariantly constant. And if you assume that C is, as it should be, real analytic in Y variables, through the expansion in powers of Y, you can find that this equation contains the Klein-Gordon equation plus all Spin-S-Bargmann-Wigner equations. So truly, this equation already contains all the free dynamics in terms of curvature. And the second equation is the actual gluing via a specific cocycle given by this operation here of the one form of the gauge fields of the theory to the actual propagating local degrees of freedom in the 0 form. So somehow, while the physics is already all contained in these equations, this equation turns on gauge fields and is the starting point actually for the dynamics, the nonlinear dynamics formulated in terms of the gauge fields as well. The interesting thing that I have no time to show, of course, but it's an old result by Misha Vasiliev, is that these two equations together contain actually the Fronsdal field equation. So these are proper free field equations on anti-de Sitter, and can be taken as definition of Fronsdal fields. And they have been derived, let me remind you, in normal order here. This is what we will refer to. One can proceed actually to arbitrarily high order in principle, then solve for the higher orders in this fashion, and plug back in the pure space-time equation, generating higher and higher vertices here in terms of W and C, which are contain the physical fields. So these would be indeed the sought-after space-time high-spin field equations, but they're really hard. And also going to the higher order via this frame of resolution, this resolution frame is pretty difficult. So, first of all, let me say that, of course, I already mentioned, but a crucial condition for this solution to make sense is that C and W, in order for them to be actually generating functions for gauge fields and curvatures of physical gauge fields, they have to be analytic in Y, of course, because you want to extract components from the Y expansion. The ordinary perturbative analysis achieves this by requiring that all fields are real analytic in Z and Y. But we will see that there are advantages to soften a bit this condition. Plus, there are no interesting exact solutions that force us to do so. And that's not, the point is also that the main disadvantages of the standard perturbative scheme is that, first of all, the vertices, writing them down gets harder and harder. And also that there are no localities already at cubic order. And also it is unclear how to select different solution spaces by imposing asymptotic boundary conditions here. So for this non-locality problem has been recently addressed to by this trick of not having the simplest possible Q star operator, but consider some shifts. And a specific shift actually is shown to admit cubic vertices in local form, and certain types of quartic vertices can be cast in spin local form, as it is called. So some sort of locality in Y space instead of X, but still that gives hope of having some criterion to control some form of locality. And this is a specific shift via this particular vector here in a specific limit for this parameter beta to -infinity. Here, on the other hand, I would like to briefly talk about another kind of shift one can make, same actually, identical, but in another limit for this parameter beta going to 1. Why? Because as I will show you, this has the similar effect to solving the equation by separating the non-commutative Y and Z variables, therefore greatly simplifying the analysis. The price to pay will be that we will have to deal with some irregular star product elements in intermediate steps. But the advantage is that the perturbative series gets much easier. And then one can make later on contact with the physical gauge in which gauge fields are actually turned on and glued to the zero form fields, to the curvatures, by building perturbatively gauge transformation. And this actually gives room to imposing boundary conditions, asymptotic boundary conditions. Okay, so what can be referred to as factorized perturbative scheme proceeds as follows. It's based on two observations. Number one is that at first order, the equations for phi are always such that phi is at first order Z independent. It's solved purely in terms of a physical X and Y field depending on X and Y. And also other equations, this is covariantly constant. So this bit here, it's easy and already contains essentially all the physical information on curvatures in the first order. The second bit of information here that's relevant is that the source term that triggers orthogonal linear correction has this form, phi star kappa, as you have seen, essentially modulo constant factors. And this phi star kappa, remember, kappa is factorizable in a Y-dependent piece and a Z-dependent piece. And I can actually reassemble them into an object which contains the whole y dependent, times kappa z, which turns out to contain all the z dependents of this non-trivial source term. That means that if I keep the y and z dependence factored, all the field-dependent data will turn out to be in psi and will purely be at first order, just y dependent through C and through kappa y. Whereas the z dependence of the source is always universally given the first order by this kappa z. So if I organize my perturbative expansion in powers of this psi, keeping y and z dependence factorized, I can actually have a chance to solve the z dependence universally, irrespectively of what are my actual fields here that are contained in psi. I can solve independently for the z dependence as long as the y and z dependence keeps factorized, separated. And to do that,
excuse me, you have 5 minutes left until the official ending of your talk. So
yes, thank you.
Keep in mind.
I will, yes, thank you. I will accelerate somehow, skip certain details. Okay, so the idea then is to use a factorized contracting homotopy. So a Q star such that, different from the one we use in the standard perturbative series, and such that it essentially, when operating on a function which is a star product of pure y-dependent piece and a pure z-dependent piece, it jumps over the y-dependent piece and only operates on the z-dependent piece. By the way, this particular operator reduces to the standard cohomology, Q star operator used in the standard analysis once operating only on z-dependent fields. That's why you will keep seeing this QE. An equivalent way of saying this story is that we can solve with the standard homotopy, but in Weil order, because in Weil order, remember, there are the symbol of this operator that I'm highlighting here has no contraction. So it's actually equivalent to the classical product of f of y times g of z. Hence, the standard homotopy will only see, that only sees the z dependence, will only operate on g. So, and either one can say we are using a different contracting homotopy operator, or one can say we are solving with the standard setup, but not in normal order, but Weil order. Okay, now here, these are technical bits. Let me only say that by pursuing this scheme, one can actually solve, arrive to solutions to all orders, which looks like this. The upshot is that U is actually remains uncorrected, just the background ADS. Phi remains, well, first order. It's first order exact. And it's the C if you want. And all the nonlinear corrections are shifted into the Z space-time connection V, which will turn out to have, in Weil ordering, which it will turn out to be irregular, because in Weil ordering, as we said, essentially the source term is going to be a delta function, and V will feel that, will be in itself an irregular element. But let's say, so be it, we can tolerate it, because after all, what we want to do is to arrive at regular fields when cast in normal ordering. Here in Weil ordering, we can tolerate some irregular operators here. At this point, the situation is that one has a solution which is entirely dependent here on what I write here in what I put in, what are the functions that I expand my psi over, so my curvatures over in Y space. And that determines and triggers the whole solution, essentially, because this part, this Z-dependent coefficient V, are solved universally for anything I can put in psi. Of course, a proper solution will only be defined by such psi and such psi that these star products actually make sense, obviously. And that gives constraints on what psi contains. Okay, however, the big disadvantage, of course, of this scheme is that, as you can see, this gives corrections only to V. Phi is first order exact, but U, which contains the gauge fields, remains background, uncorrected. There is no gauge fields turned on. As I remarked in the beginning, this is not absurd because phi already contains all the degrees of freedom of the theory. But if we want to speak about Fronsdal fields and boundary conditions on Fronsdal fields, we need to find a way to connect the degrees of freedom in U to phi. And that implies changing the resolution operator Q star, or change, this can be induced by a specific field-dependent modification to the gauge function. Instead of writing solution in terms of the gauge function L, I now change it to some field-dependent G that has nonlinear correction in terms of phi. So what the proposal is essentially now to move the perturbative problem to building a gauge function H. The first order is easily determined via gauge condition, and the higher orders will be determined by imposing asymptotical ADS boundary conditions at the level of master fields. So how this works concretely is as follows. I can take my solutions that I just determined before via this specific perturbative expansion in Weil order. And now I'm going to operate on that. So the solution was essentially first order exact curvature here, generating function C, a nonlinear V that was anyway that could be can be written in terms of this conjugation with gauge function of the background, and a trivial gauge field generating function. I change now my gauge function L to some field-dependent G. I extract the first order, and the first order leaves the degrees of freedom unmodified and changes V by a pure gradient here, and changes U by this object here, which contains the ADS covariant derivative of the gauge function field-dependent at first order. Now, without entering into technical details because there's no time, the point is this gauge function is such that, being field-dependent, it will activate non-trivial gauge field despite the fact that this looks like a pure gauge term, due to the fact that H is actually cohomologically somehow it's cohomologically non-trivial. Therefore, there will be a non-trivial part contained here that exactly what it does is that it glues precisely the fields that are inside. It gives rise to a non-trivial gauge field generating function from D0H, which it turns out to be regular because all the possible irregularities in V are cohomologically trivial. They are pure gauge. And at the same time, it will glue W, the generating field, to the curvatures phi, which will turn out to be unmodified in the first order. Hence, the generating function of the gauge field that sits in U will actually be sourced by the degrees of freedom of the original solution that we have found. This gauge function actually will turn out to be unmodified, only determined up to a piece which is of order Z square. Anyway, there's some piece which is undetermined, left undetermined by this procedure. And this is precisely a piece which can be used to impose boundary conditions in the following sense, that one can actually impose our nonlinear solution in bulk solution to approach Fronsdal fields at the boundary. What does it mean concretely? Let me just, this is the last thing I'm going to say. Keep in mind that if I expand as asymptotically my so obtained solution, the 1/r expansion, if r is a coordinate that goes to infinity at the boundary, is not necessarily coincident with the perturbative expansion in the coupling constant of the theory. So this demand that I impose ADS boundary conditions on my generating function is non-trivial because the interactions that are non-trivial on my bulk solution mix different spin. In other words, if I have a nonlinear configuration, lower spins actually may contribute through nonlinearities to a given leading 1/r dependence in the spin S field, let's say. That means perturbative expansion and asymptotic expansion do not coincide. So it is a non-trivial statement at this point to require that the gauge field at boundary, so in an expansion in 1/r, linearize and give rise to actual Fronsdal fields. And this remaining freedom of this gauge function H, in principle, should allow to do so. We have to actually evaluate it, to do it. I mean, we just started this analysis, and we have to see whether in fact this is possible. But there is, let's say, just room for it at least. And in the simplest incarnation of this, demand, essentially, the point is that in the 1/r limit, this gauge function will be such that it will allow for the gauge fields, the master fields, to actually linearize completely. So all the higher order P's in this new gauge will be order 1/r. Okay, so this is all I wanted to say. Once actually one can impose these boundary conditions, one is in a position in which one can effectively, one is in a position of comparing actually with proper, is in the standard AADS CFT setup. And at this point, so one has Fronsdal fields that will behave asymptotically as sources for operators. Prior to imposing these boundary conditions, it's far from obvious. And by the way, this type of mechanism that I just highlighted induce nonlinear correction to classical observables, which are precisely the classical observables that are used to extract boundary correlation functions. So one has to, we should try and check finiteness of these observables, of this boundary correlation function after implementing this procedure. Okay, and recently we have tried to extend this analysis to a family of M orderings interpolating between normal order and vile order fields. So, okay, I will stop here because I'm over time. Thank you for everyone for your attention.
Okay, thanks, Carlo.